Okay, hi everyone. I did record my recap and exercise section in section 570, but unfortunately the video got corrupted and I will have to remake the video here. So these are sets. We saw things about sets, and actually I actually decided to change the way I recapped. In section 571, I kind of summarized everything that we saw and then started doing exercises. But then I realized that it wasn't the best way. So in 570 and in this video, that will be available for 571, I am recapping the concept and then doing exercises that kind of are related to the concept. So what we saw was sets. We saw that we have operations as union, intersection, and complement. We saw that the empty set and the set itself are always considered subsets of A. And then we saw some equations, right? Equations regarding the elements, the number of elements inside a set, right? So we're dealing with counting problems, and we want this equations, this n here, you have to read this as the number of elements. And whatever comes in parentheses is the set you're talking about. So the number of elements in this set, this composite set here, given by x union y, is equal to n of x plus n of y minus the number of elements in the intersection. And I'm using x, y now because on both sections there were confusions. I was using a and b, and then some students were confused when to use a and b. So I'm using x and y right now. So these equations are valid for all x's and y's, okay? You could set a problem where x is a and y is b, or you could set a problem where x is a, b and y is a, okay? Like it depends on the problem. So we have this equation. The equation of the intersection is a dual equation. So if you know one, you know the other, because they are kind of similar. And this is the equation for the complement, right? It's the number of the universal set minus whatever is inside the set you're talking about, because you're taking the complement. And there's another equation that this one is not so intuitive, and we will use it in an example soon. Is that the number of elements in X is equal to the number of elements in X intersection Y plus the number of elements in X intersection Y complement. So given that you have a problem with two sets, X and Y, the number of elements in X can be calculated by these two numbers here, okay? Then we saw the De Morgan's laws, where to remember, you just kind of let the exponent drop, and you flip the sign. So this is, I just passed an error here. So flip the sign, okay? And then we saw trees, okay? So trees are things that they are summaries of decisions. So each layer of a tree is a decision that you make, and each branch are your options. And we saw trees that were set for sets and counting normal counting trees. Okay, so when we set up trees to analyze sets and their elements, we set up a tree in this particular way. You start on the universal set and you branch on whatever set you have. So an element will be in, you can have an element that is in A or an element that is not in A. And this is the characteristic of the tree for sets, is that you branch only in two options. And you always move to the next layer when you're asking the question of whether you have, or whatever you chose to be in B or not in B. Okay, so if you chose to be in A, you're an element of A, and then you're an element of B if you're sitting here. So you have this path of decision is A, this green path here is A, and then B. Okay. And then we saw that this tree set up for sets, they have special properties. One of the special properties is this. Whatever is coming into, so actually, I'm not sure if I'm going to go. Yeah. So one of the things that we have to understand is that the number in the branch, this number regards the set, the path, right, that you formed, the set that you formed by pursuing this path. So for example, if I show you this tree, 15 are the number of elements of, so 15 is the number of elements of A intersection B. The paths are the intersections because you have to be in A and then have to be in B. This is 15, okay? The number of the elements in A is 20. Okay, it's an intersection, but I don't intersect with anything before. So it's N of A is this branch here. Okay. Some important properties. Whatever comes in a node has to come out. So if I have 50 elements in the universal set, this breaks to 20, this necessarily has to break branch with 30 elements, okay? Because 30 plus 20 has to sum up to 50. The same thing as here. If I'm sitting in A, there's 20 in A, right? It's coming in 20. So if I'm sitting here in A, and I branch, for example, if I branch to 15 in B, I will have necessarily to branch 5 to B complement, okay? Because 15 plus 5 is equal to 20. And the other property is that every path that passes through a node, if I ask you, for example, what's the number of elements in B complement, you have to consider all the paths that passes through the node. So I have two nodes, okay? I have two nodes, two paths, sorry. So 5 plus 20. So I have to account for 25 because I can be in B complement through A, right? And I can be in B complement through A complement. Okay, so these are the most important properties. So given that this will be in our toolbox, right? This will be in our inside our toolbox. When you read some kind of question like this one here, you will look at your toolbox and say, okay, this is a set question, and I can tackle this problem either using equations, because they're asking number of elements, or using trees, because trees substitute all those equations because you can count the number of elements in each branch. So I will solve this problem both ways. So the question is, determine the number of elements in A union B, okay? And I have some information. N of A is 30, N of B is 40, and this intersection here is 15, okay? That it's A complement intersection B. So I'm going to copy this information, or actually better, I'm going to copy this to here. And then we're going to solve this in the first way we're going to do it is using trees, okay? You will see that by using trees, you can easily find the answer. I'm going to do in a very slow fashion. So you have your universal set, and I have two sets, A and B. So I'm going to set my tree, like I said, branching on each element, on each set, meaning that my elements can be in A and then in B, or A and B, A and not B. It could be A complement and B, and A complement not B. So each layer is a set, each layer is a decision of whether an element, a particular number of elements are in the set. And then the second decision would be the second set that I'm choosing. And also I always branch into two possibilities. So whether I chose to be in A or in A complement, in the next layer we'll have to branch 2 times. Okay, so let me complete this. I have some information. Let's complete this tree. N of A is 30. And N of B is 40. Now, should I put N of B here? No. Why? Because I actually have 2 ways to be in B. I have 2 paths, right? I have 2 paths to be in B. I can be in B by this path, and I can be in B by this path. So everything that comes into the node has to be accounted for. So whatever number is here or here, it has to sum to 40. So I'm going to just take a note about this, right? B is 40. Or I could call X and Y, but I can also take this note, a side note. And the other number that we have is that A complement C union B is 15. So A complement B union, A complement intersection B, sorry, A complement intersection B. So this, exactly this branch here is equal to 15, okay? All right, so this is my tree, and I kind of completed all informations that I have, okay? All right, so how can I start thinking about this problem? I know that everything in B sums up to 40. So whatever is here plus whatever is here has to sum to 40. And I already have 15 because this was given. So how much do I put here to get to 40? So 15 plus 25 will give me the 40 elements that are in B. Okay? Now, after I found this, I can use a rule of the tree where I have 30 elements in A, so I necessarily will have 5 elements in this path, okay? Because the 25 plus 5 has to sum up to 30, okay? And what's the question that I want? What do I want? Well, I want the A union B, okay? So I want, what does that mean? I want to know how many elements are in this set given by the union. Remember, what's a union in a tree? A union means that you can have a path or another path, or you can have a set or another set, and you're good. Both of them work. So I want to have a set A. I want the number of elements in set A. Or in set B. So this is the path of set A, okay? And again, like if you think about, both of these paths are part of set A, right? Because it's branching. 25 plus 5 is equal 30, obviously. So these paths are the paths of set A. And the paths of set B are this one here. So I can have B here. And I can B and B through here, okay? So these are my sets, okay? I have to count the elements of these paths, okay? That's what I'm asking for. And I have to account for both paths, because both of them are good for me. It's a take-it-all set. So let's account in the blue path, which is the path in blue, and this one, which is the path in, this is the path in pink. So the path in blue gives me 30, right? Or 25 plus 5. I'm accounting for both ways here, okay? Which is the complete 30 from A. And to account for B, the number of elements in B, well, let's account the pink parts, right? So the pink parts are the 15 here, and actually this 25 too. But do you agree that whoever is here, if you're sitting here, you are in either A and B or in both? So I already did count for these people. I don't need to put plus 25 here, okay? Because that will be a double counting. So I'm counting the elements of sets, and sets are the path. I'm counting the elements of A, which are the blue path, passing through A, and I'm counting the elements passing through B, okay? And I want to count how much people I have in all of these sets. So pink sets and blue sets. So I account everybody, but if I count this 25 again, I would be double counting, okay? Because imagine that Louisa is here and you already count me, right? You already count me in set A, but I'm sitting on both sets. So if you count me again, you will be double counting. So this is one way of solving the question. And actually, we didn't solve the sum here. This is 45, right? So n of A intersection B would be 45. So this was how I solved in class. It's the same way that I solved, so that you can keep both slides, okay? Now I'm going to solve using the equations. Okay. So here's the information here. So you're going to start using equations. Here's the information. You go to your toolbox. This is a set. I'm going to use equations. So what equation should I pick? I will pick the first one because this one gives me a union, and it gives me explicitly how to calculate an union. And it doesn't matter here, like this is A union B, or it could be B union A. We know that this is commutative, okay? A plus N equal to B minus N of A inter B, okay? And it could be B inter A, it doesn't matter, it won't change, okay? They're commutative. Now I have this, I have that, right? It was given to me, this is 30, this is 40, but I don't have the intersection. So I have to find, in equation 1, I have to find this intersection. What equation will I use to find that intersection? Okay, I will use, I can't use this one because this one, I will have to use the union at some point, and I don't have it. This is exactly what I'm asking for. So I will use this one, okay? Why? Because the intersection appears here. This is what I want. And actually, if you take a look at this intersection, there is a set that is, y here is, there's a complement in y. So for example, if I set my x to be, and remember, this is an intersection, is commutative. Actually, this could also be written as y complement inter x. So if you think about it, if I set for this equation, so if I call x, b and y a to use in this equation, right? And you would come up with the result as n of b is equal to n of b inter a, right? Plus n of b inter a complement. Okay, I want this. I have this, n of b is 40, and I also have this. See, it's commutative. It doesn't matter the sequence, but I managed to put my a. I managed to find an equation where I will find the intersection, and then I will put the intersection here in equation 1, and then find the union. Okay, so let's solve this. N of b is 40. This is what I want. B inter a, or a inter b is the same thing. Plus this is 15. Okay, and when you do solve this equation, this is 25. Okay, so now back to equation 1. This was equation 2, obviously. I will finish it. So A union B, I'm going to substitute already. So n of A union B is what I want. This will be n of A, which is 30, plus 40, which is n of B, minus 25. And if you do the math, this is 45. Okay? So you can think about, when you look at these equations, you can think about setting x and y equal to a or b, and it doesn't matter that much in equations like where like you don't have even the complement, because you could be b and a, whatever. In this one, you want y to be a, because you have the information, right, that a appears with the complement here. Okay. All right. So this is how I solved in session 571. This is the same thing. Okay. Now we're gonna solve another problem regarding trees. Okay. Another problem regarding trees, and this was the solution for the session 571, but I'm going to do it all over again. Okay. So here's the problem. This is a test problem. It's very similar to what you will see in the midterm. So a wildlife conservation organization tracks 3 types of animals in a nature reserve: elephants, lions, and giraffes. The organization monitors the population to understand how many animals of each type live in the reserve and how they overlap in different areas, and gives us some information. Okay, so when you look at this kinds of problems, and you have all these information. And the question is this: in total, how many areas in the nature reserve have no elephants, no lions, but do contain giraffes? You have to interpret this problem as a set problem. Why? Because you can have both things, right? You can have several combinations of elephants. You can have elephant, lion, and giraffe, no elephant, no lion, and giraffe. So what you're doing is you're dealing with a set problem. And the way we're going to make the solution of the set problem is by using a tree. And you can try to get these equations done, but I have 3 sets. And then it would you would have to do partially, and it would be nasty. Okay, so that's why it's so important for you guys to train counting trees. So this is a set problem, and I'm going to set up my tree using like the setup that we know. So I'm going to consider E as the elephant set, L as the lion set, G as the giraffe. So I start branching my universe, okay? I have areas. This areas, right? Because the problem says that there's an organization that monitors these animals, and we're going to keep a track in whether areas have these animals or not. So this is my reserve, or my lands, or right, my areas. And I can branch. Some of the areas can have elephants. Some of the areas don't have elephants. This is my first set. Now, as we know, the sets when we set up a tree for sets, we branch just only one time for one set, and then we keep going to the second layer, branching to the other sets. So then I'm gonna branch. It doesn't matter if my reserve has elephants or not. I can have now lions or not lions. Lions or not lions. Okay? And then as a final branch, I will branch into giraffes or not giraffes. Giraffes or not giraffes. And giraffes and not giraffes. Giraffes and not giraffes. Okay, so think about this. Let's do this path here. These are areas that do not have elephant, do not have lion, do not have giraffe. I don't know, maybe as I said in section 571, maybe the grass there's no grass there, so the elephants and giraffes can't eat, so they don't go well there, and then lions also don't go well because it doesn't have elephants and giraffes to eat. You could have a reserve where you have all elements, an area that you have of the reserve that you have all elements, or you could have, for example, you have an area that has elephants, don't have lion, and have giraffe. Okay, so this is my set. This is my tree for the set. And the question is, how many areas in the nature reserve have no elephants, no lions, but do contain giraffes? So this is the path I want to know. Whatever number sits here is my answer, right? Because this is it's kind of passing through this path, which is this intersection, okay? So let's start filling up, completing this tree with the information. So I have 28 areas in the reserve that are home to elephants. So 28 comes here. 24 areas have lion. Okay. So should I put it here? No. Should I put it here? No. Why? Because I don't have a single path to lion. Lion will be a composition, right, of people that are in lion and in E, and that are in lion and not in E. So I have to account for these 2 paths. I can call X, Y, whatever, but I'm going to put here aside that this is 24. Lion is 24, okay? Then I have an information that 25 areas contain giraffes. Well, again, I can put A, B, C, D, whatever, X, Y, Z. You can call this branches names and say that the sum of these variables are 25 because there are 4 options to go to giraffe. But I'm just going to say, okay, there are 25 areas that has giraffe. I'm kind of just explicitly putting here this information so that I don't forget. Now, 3 areas have all 3 animals living in them. So 3 areas have elephant, have lion, and have giraffe. So this here is the number of this intersection, of this path, okay? Now, 2 areas have none of these animals, meaning that that area that has no grass, this no elephant, no lion, no giraffe, has 2 areas, okay? Okay, so then 8 areas contain only elephants, meaning that I have elephant. And this is a common mistake. I see lots of students kind of putting here, like if this information was not given, putting here, oh, I have 2 areas, sorry, 8. I have 8 areas that only contain elephant. But this is not right, right? What we need to do is to consider the only here. I only have elephants. So this is not what we're saying. We're saying that I don't have elephant, I have elephant, and I don't have lion, and I don't have giraffe. Because I could have elephant, and have lion, and have giraffe. So this only here is very important. Okay, so this is the path. And we have 8. 5 areas have only lions. Okay, let's do the path, right? And I'm gonna get rid of this. So there's a path that has only lions. So I don't have elephants, I have lions, and I don't have giraffes. So this branch here is 5. Then there's this information. There are 50 areas for the reserve in total. So my universe has 50 areas. And 15 areas are home to elephant, but not lion. Okay? So let's think about this. In this area, I'm home for elephants. So there are elephants, but not for lions. Okay? I don't have the information about the giraffes. It could either have giraffes or not, but this path up until here is I have elephant and not lion. This is 15. Okay? Cool. So now let's try to complete this counting tree. First of all, 50 is in the universal set, and I'm branching 28. So to get to 50, to sum up to 50, this should be 22. Okay, 22. All right, what else can I do? Well, I can do this. Look, 28 is branching to 15. So I have to put a number here that this number plus 15 gives me 28. So this is 13. Okay. What else could I do? Again, let's use the rule, which whatever comes in the node has to sum what gets out. Here is 15. It branches 8. So I have to put a number here that when summed up to 8, it results 15. So this is 7. Okay, I used like one of my rules to trees. Now, what else can I do? Well, think about this. Lions, let's use the other information that is missing. I have 24 lions. So everything that goes in lion, like the node the branch that it goes into lion, has to sum up to 24. And I have 2 ways. to be in line in this path or in this path. This path, I already have the number, is 13. So whatever I have to put here has to sum up to 24. So this is 11. Okay, because 13 plus 11 is 24. What else can I do, or can I use of information? Well, now that I have this L, I can break this into 6 and 5. Okay. And again, if I have this information here, this L here, I could break this into 10 and 3, right? Another information that is important is 22 is coming in this node, and then I'm branching out. So this is also 11, okay? And now I'm going to use information, important information, that giraffes. So I kind of went all through the. I've used this rule and then again filled the ones that I could by the branching rules. Now I'm going to use this rule, that giraffes sum up to 25. So I have 3 giraffes here, 7 giraffes here. This sum up to 10, plus 6 giraffes here. Okay? That sums up to 16. So whatever number comes in here, okay, because all the paths that goes into giraffes has to be accounted for, and the sum of this paths needs to be 25. So up until now, I have 16. So whatever number I put here has to sum up to 16 and result in 25. So this is 9. And now our answer is, well, the number of this set here, no elephants, no lions, and giraffes sums up to 9. Okay? So this is another kinds of exercises that type of problems that will be asked in the midterm using trees. Okay, so it's very important for you guys to know how to use the trees and all the rules. Okay, so this was the thing I solved before. Okay, so now we're going up until now we did this. The item 1 of our toolbox is sets and the equations, and the second tools are trees that are set up to sets. Then I'm going to continue growing our toolbox. Number 3 is trees that are used for counting problems, right? So it doesn't mean that I have to branch just only in 2 possibilities. I can have more possibilities. For example, if I want to choose a dog 1, dog 2, dog 3, right? And I know that each layer is a decision, and my options are the branches, right? So for example, dog 1, dog 2, dog 3, okay? And there are 2 rules to use these trees for counting problems. First rule are if you're taking sequential decisions to calculate the number of possibilities that you have to make a decision, you have to multiply the number of options in each layer, okay? So if I have 3 dogs and 2 cats, first I'm going to select the dogs, then I'm going to select the cats. This will be 3 times 2, 6 possibilities, 3 different ways that I can select. I could select dog 1 and cat 1, dog 1 and cat 2, dog 2, cat 1, dog 2, cat 2, dog 2, cat 1, dog 3, cat 1, dog 3, cat 2. So I have 6 ways, right? I'm counting 6 ways by multiplying the number of options in the first layer times number of options at the second layer. So I have 1, 2, 3, 4, 5, 6 different ways, because these are sequential decisions. And there's another rule named the addition rule that is a tool that we use when you're not doing a sequential decision, right? You're doing a single decision, and it's usually done when you say that you're okay with one or another. So for example, let's say that I go to the pet shop and I'm not taking 2 pets, 1 dog and 1 cat. I just want a dog or a cat, right? I'm gonna leave the store with only 1 pet, and it's take it all. Like, any option is good for me. So I can make a decision, right? I can make a decision like dog 2, but I had 5, 1, 2, 3, 4, 5 options. So which is formed by 3 plus 2. So I add up the options, okay, that I have in each variable. So if you have a variable dog or I have a variable cat, just do 3 plus 2, which is 5, okay? Again, what we're doing with trees is counting the number of overall possibilities. Obviously that you will do one path, you will go through one path, like I selected a Schnauzer and a white cat. You did this selection, but you had 6 different possibilities, okay? So a particular consequence of trees, so this is 3.A, it's what we call selection with replacement. This is actually the multiplication rule, but it's a very common thing in counting problems. So it's good to kind of know what it is and how to tackle it. So selection with replacement is all about you have 3, like let's say that you have a bucket and you have a red, green, and blue balls, and you have, I don't know, 7 people coming in and choosing a ball, choosing a color. So what will happen is the first person takes a blue ball, and this is the first decision layer. So the person will have 3 options. Then the second person, before the person comes in, I ask for the first person to return the ball, right? That, let's say that it took a green ball, it picked up a green ball, and then I say, okay, yeah, you're green, you went this way, but put the ball back. Right? Why? Because the next person, the next decision will branch in 3 possibilities again, right? Red, green, and blue. So this is if you apply multiplication rule, you will be 3 times, 3 times, 3 times, 3 times the number of decisions that you have. Okay? And this is called selection with replacement. So now I'm going to do an exercise. I'm going to solve an exercise here that you will see. It's a quiz question that you use this concept to solve. So what you have here is, and actually it will solve the first part of this question. Now we will come back to it. So a finite mathematics course has 30 students in it. As a final project, the students are assigned a topic in finite mathematics: counting, probability, discrete random variables, and continuous random variables, and must give a 10-minute presentation on their topic. So the instructor must assign each student a topic. The question doesn't stop here, okay? So this is just the first part. The first part of the question. The question goes on. In how many different ways? So the instructor must assign each student a topic and draft a schedule, right? So the instructor must do two actions. First, assign students a topic. And then we will have a subsequent action, but let's solve the first action, the first task. The first task is to assign each student a topic. So think about this. This is a selection with replacement. Why? Because I have a theme 1. I'm not going to use these names. Theme 1, theme 2, theme 3, theme 4. Okay? And think about this. It's like I have the bins of each student. I have 30 students that I'm representing as bins or layers of decision, layers in a tree. So what's the first layer? I have to assign, or I have to select, or I have to decide. I have 4 options for my first student. Okay? So let's say it took theme 2, and whatever it took, like theme 2, the next student and the next decision will have also 4 options because they're not excluded. It doesn't mean if the first student took theme 2, it doesn't mean that the second one can't, right? So, for example, if you continue this branching, this tree, you would have a particular path here that will be, oh, I'm taking theme 1, theme 1, theme 1, and going on 30 times. That's a possibility that every 30 students chose the same theme. Okay. So, but what are you doing in terms of possibilities? Obviously that you will take one path, right? But how many different options did you have before, like the overall number of options? You took a path, but the overall options were, I had 4 options in the first like in the first layer of decision. Then I had 4 options in the second layer, and 4 options in the third layer. These are subsequent events. So I call student 1 to pick a theme, or I assign a theme to student 1, and then I ask student 2, and then I go and assign to student 3, and so on. I'm just doing this as a scratch, right? I'm not doing the right. If you the selection with replacement, the correct tree would be this, right? So every layer, for every single node, I have the same options, right? So I'm just doing this to kind of remember, so that I can remember that are 4 layers and 4 options. So in the end of the day, this is 4 to the 30th, or n to the k, where n is the number of options and k is the number of decisions or number of selections that you do. Okay. And I stopped there, and we're gonna begin talking about selection without replacement and permutation in the next lecture.